We're excited to have Alison Gopnik up next. Many of us are very excited as we have increasingly capable low-level perception and action systems to try and move towards human level, or at least child level AI, and Alison will speak to that.
Okay, thank you. Okay, so part of the point I want to make is that that at least is wrong, that in fact what we could get if we understood child intelligence would actually be more powerful than what we typically think of when we think of adult intelligence. And that's actually one of the points that I'm going to make. So in the famous Mind paper in which Turing first talked about using the imitation game as a way of trying to decide whether a system was intelligent, just after he's had that discussion, which everyone quotes, he segues to this extremely interesting comment, which is that maybe instead of trying to produce a program that will simulate the adult mind, maybe instead we should try and produce one that simulates the child's. And in typical Turing fashion, he goes on and says a bunch of really insightful things about this. Why does Turing think that simulating a child might be a better route than simulating an adult? It's because what children do better than anything else is to learn. So if we could actually design a system that could learn all the things that we know from data, that's actually the key to human intelligence. And for many years, this comment of Turing's was just sort of neglected. Nobody paid any attention to it. But in the last 10 years or so, people have started to take it much more seriously. And there's a reason for that, which is that the great increases, the great achievements of recent AI, the ones that have drawn all the attention, have really focused on Turing's point of trying to design systems that can learn. So not just design systems that have hand-coded all of typical adult intelligence, but have systems that actually can learn from data. That's been the big excitement. But the problem is that those systems are things like deep learning, reinforcement learning, supervised learning. The trouble is that those systems have a lot of restrictions, and I think after the first excitement about how much the systems can do, we're starting to see some of the barriers that those systems come up against. So an obvious one is that they need lots and lots of data. So they only work with enormous amounts of data. And in fact, it's having that enormous amount of data that's made these systems tractable. And they don't often do very much, or in particular, the right kinds of generalizations. So even if you can train up a system to, say, do very well on classifying cats and dogs, the system will have trouble if you just change the parameters in what look like not terribly deep ways. And even more significantly, as you know from these kind of adversarial examples, there will be cases that it will just get dramatically and completely wrong. And even worse, you have the problem, the ubiquitous problem of catastrophic forgetting, where you can train a system to do one thing, and it seems as if you ought to be able to use that to solve another problem, and instead you have to start all over again from scratch. On the other hand, the big advantage of these systems is that they're computationally tractable, so you can actually more or less make them work. In contrast, if you look at every human two-year-old, two-year-olds learn very rich, abstract, generalizable structure. They learn a grammar of their language. They learn theories of everyday physics, of everyday psychology. They make excellent generalizations, and they have very little data. So they can learn with only 2 or 3 or 4 examples, nothing like the kind of data sets that we've typically used in AI. And they make very good, broad generalizations from that very small amount of data. And a way that we and others have characterized this, in particular in my lab over the last 15 years, is to think about what the kids are doing as a process of Bayesian inference of hierarchical, probabilistic, structured causal models. And that turns out to be a good description of what the children are doing, but it has one big drawback, and the big drawback is that it's computationally intractable. So actually trying to search through the entire space of any kind of interesting hypothesis or any interesting high-dimensional problem turns out to be incredibly difficult computationally. So I think we're at a point where what we'd like to do is to design systems that have the characteristics of children that can make great generalizations from very little data, but make systems that are actually computationally plausible. And I want to emphasize that the very fact of childhood seems to play an important role in this human ability to develop great generalizations from very little data, this human ability to have particularly resilient, robust kinds of intelligence. One of the things that's interesting about human beings is that we have twice as long in childhood as any other species. So chimpanzee is producing as much food as they're consuming by the time they're 7 years old. My son is 30, and humans are not. There probably are even people in this room who are still relying on input from their parental caregivers. That's a very puzzling thing. That looks paradoxical. But it turns out to actually be interesting because across many different species of animals, mammals, birds, even insects, there's a correlation between this extended period of childhood and adult intelligence, and particularly the kind of adult intelligence we would really like to have in computational systems, adult intelligence that is flexible and robust and can learn a great deal. So if you look at different species of birds, different species of insects, different primates, this very long period of childhood seems to play a particularly important role in intelligence, even though it seems sort of counterintuitive and paradoxical because we have to put so much investment in these children. And you see something like this if you actually look at brain development as well. So this is a famous graph showing the way that synapses connect. And what you see across many different species, very characteristically, is this very distinctive pattern. This is the number of synapses and connections that are being formed. And what you see is that there's this early period when many, many new synapses, many new connections are being formed. The system's extremely plastic, flexible, sensitive to data. And then there's a kind of tipping point where the connections that are used a lot become longer, they become stronger and more efficient, they're myelinated, and the connections that aren't used are pruned, they disappear. And that tipping point is different for different parts of the brain in a way that reflects cognitive development. So the visual system, by the time you're about 1, this tipping point has happened. For things like the frontal lobe, it doesn't happen until quite late. And in addition to that, particularly in humans, you see this process where the prefrontal areas, the executive function areas, the areas responsible for things like goal-directed action, gradually get to have more and more control over the rest of the brain. And I think it's really interesting that this architecture, which is ubiquitous in nature, is not a typical architecture that people have used when they're trying to design AI systems. So we don't typically have the sense of different developmental periods with really different functions. What might this kind of architecture serve? What's the point of childhood? Why do we have children at all? As I point out, sometimes when I give this kind of talk down in the valley, it's not completely clear that people in the audience have figured out the proximal obvious answer to that question, but presumably people here have more or less got it. But the broader evolutionary question is, what kind of function does it serve to have this kind of developmental trajectory? And the argument that my colleagues and I have been making is that this really reflects a very general idea that comes across in many different domains. This is this idea of exploitation versus exploration trade-offs. So one of the great challenges of trying to get a system that's going to get to a good solution in a high-dimensional space is that you can either try to find a solution quickly and efficiently, but then risk getting stuck in a local optimum and not finding other solutions that might actually in the long run be better, but that require more exploration to get to. One way that this is often cashed out in optimality theory and in AI and in neuroscience is this contrast between having a low temperature and a high temperature search. So a low temperature search, you're trying to find a solution that's quite close to the solution you already have that, say, will score well on your whatever your measurement of success is. But the result of just looking at things that are pretty close to where you already are is that you might miss a much better answer that's much further away in the space. On the other hand, if you have a high temperature search, you're going to consider many, many, many different kinds of solutions, but you're going to be spending a lot of time, essentially that time of childhood, looking around trying to solve problems and not having the solution that will get you the high score or enable you to achieve. And one of the my kind of slogan of the work that we've been doing most recently is to think about childhood as being evolution's way of resolving these explore-exploit trade-offs and essentially performing simulated annealing. What you can do is start out with this high-temperature exploratory kind of system, which is not actually going to do very well on any immediate measures of success, but having that period is actually the thing that enables you to design more flexible and resilient systems as you develop. And that's actually reflected in the differences that you see between adult intelligence and child intelligence. So if you think about that as the general architecture, what you might expect is that children are particularly adapted to be very good at things like wide-ranging exploratory learning. And in fact, that's what seems to come out of the psychology. So what might be some features of this kind of childlike learning that would help to solve these explore-exploit trade-offs? And I think there's a number of different ones. One that we know from empirically is that children are not starting out as blank slates. They're already starting out with high-level abstract representations of the world, literally from the time they're born, and we know quite a bit about that. We know that children aren't learning in isolation. They're learning from other people, and we know that they have really striking capacities to interpret information that comes to them from others, again, in contrast to most AI systems. The one that I'm going to emphasize today is that we know that children are actively learning. So rather than simply sitting there and taking in data, or rather than simply attempting to, say, maximize a particular reinforcement schedule, we know that children are actually going out and actively trying to get data about the world for no other reason than to increase their understanding of the world. And let me give you a concrete example of this using the kinds of, how could we say this about kids? How do we know this? Well, we've developed a whole lot of techniques that allow even preschoolers to show us just how good they are at considering hypotheses and solving problems. And let me just give you a little video that can demonstrate this. So, oops, sorry, do we have sound for this? Can we just do it this way? I'm sorry, I should have mentioned that. Can we, sorry. Oh, we do. Okay, great. Let's do that. And we'll start over again. So let me explain this to you while we're doing that. So how do we show that children can make these incredibly elaborate inferences? If we asked them, they probably wouldn't do very well. What we can do is actually show them a real-life example. In this case, it's something we call the Blicket detector. It's a little box that lights up and plays music when you put some things on it, but not other things on it. And this little boy has seen before that red things make it go and yellow things don't, and now he sees an anomaly. He sees something that looks like it doesn't make sense. There's a yellow one that goes on and it doesn't work. And what we do is just leave him alone, leave him there with a box and see what he does.
This on the box and this on the box. Look.
Uh-huh.
This makes that light up the box.
Mm-hmm.
How about this? That makes the other side. Uh-oh. Nothing. This one's lighting up and this one's not. So that means... What's making this light up? I don't know. Oh no. Oh, it's because this needs to be like this. And this needs to be like that. That's why. Oh. Probably the boxes are the wrong way.
So this is his suggestion for the next thing to do.
What should we do now?
Oh, because the light goes only to here, not here. Oh, the bottom of this box has electricity in here, but this doesn't have electricity. It's lighting up. So you need to put 4. So you need to put 4 on this one to make it light up and 2 on this one to make it light up.
Okay, so that's a particularly adorable little boy, but it turns out that his behavior is actually quite characteristic of 4-year-olds when you give them this kind of problem. And you can see that it's exploratory and curious in 2 interesting ways. One way is that he's producing this very wide range of active behaviors to try and get the data that's relevant to the hypotheses that he's trying to solve. So he's going out and actually getting the right kind of data rather than just waiting for the data to arrive. The other thing is that the range of hypotheses and solutions that he's considering is extremely wide. And he's moving from one solution to another in this very broad, wide-ranging way, thinking about things like number and shape and size and color. So he's treating this problem as if it's a high-dimensional space. And what he's trying to do first is figure out what are the big, broad borders of this space before he goes into the details about the objects. And as you can see, there's no reinforcement going on. He's not getting any immediate reward for doing this. None of these things are working. If he was trying to just make the box light up, it would make much more sense to try to stick to a particular strategy and just continue with that strategy. And that turns out to be really characteristic of children. And what we've seen in a bunch of experiments that we've done is that, in fact, if you compare this kind of behavior to adult behavior, the children are both more exploratory and curious in the sense that they're being more active, they're actually doing more, and they're also considering a wider range of solutions than an adult typically does in this kind of experiment. And I'll just quickly go through the most recent experiments that we've done with this, where we've actually specifically been pitting exploration versus exploitation. So what we do is very simple. We have a kind of reinforcement learning paradigm where now we have a Blicket detector and an object goes on the Blicket detector, and if it's one of these 3 objects, you get a sticker, and if it's one of those objects, you actually lose a sticker. And as you can see, the issue with this, and you get one object at a time, what adults typically do in this case is if they see that yellow striped thing makes them lose stickers, then they won't put anything that's striped or anything that, that this black striped thing makes them lose sticker. Now they'll avoid anything that's black or anything that's striped. And if all you want is to try to avoid the loss, that's actually the sensible thing to do. That's actually a good exploit strategy. But of course, the downside of that is that you're never going to find out that this other object actually could be gaining you stickers. You're going to end up with a too restricted picture about how this, you're going to end up with the wrong picture about how this system works. So what we did was just do exactly this experiment with 4 to 6-year-olds, 6 to 7-year-olds, and adults. And what we saw was that, as you might expect if you have ever tried to keep a 2-year-old or a 4-year-old from killing themselves, the 4-year-olds are perfectly happy to try things that will have immediate negative outcomes in the interest of getting more information about the system in the long run. And indeed, that's effective. So that, whereas the adults, as I said, are so concerned about trying to avoid the loss that they don't actually do the exploration. And as a result, when we actually ask them about how the system works, the 4-year-olds are getting the best account of how the system works, and the adults are getting the worst account of how the system works. And there are lots of other examples like this where we've demonstrated and others have demonstrated that younger learners are actually more exploratory. And that's part of this evolutionary setup where the losses don't count in the same way if you're 3, because your utilities are determined by the caregivers who are taking care of you. You don't have to worry about losses and gains when you're 3. I always say 2 and 3-year-olds have one utility function, which is be as cute as you possibly can be. And they're extremely good and effective at maximizing that utility function. And as long as you do that, everything else follows. You can do whatever you want and not worry about exploitation. So if this picture is right, many things that we think of as bugs typically of children, things that people have thought are signs that children are dumb or irrational or are random, might actually turn out to be features from this exploratory curiosity picture. And that might be very relevant if we're actually trying to design artificial systems as well. Again, the temptation when we're trying to design an AI system is to do something like get it to have the highest score on Mario Brothers as quickly as possible. And what this suggests is that things like noisiness, variability, randomness, not having very good executive control, not being very good at inhibition and focus, spending a lot of time engaged in play that doesn't have any kind of obvious payoff or any kind of obvious benefit. All those things that are so characteristic of young organisms in general and human children in particular might actually be things that are helping to solve this explore-exploit trade-off and mean that when you do have a solution, that solution is going to be more robust and generalizable in the way that the human solutions are robust and generalizable. And a thing that we've been particularly working on right now in collaboration with Pulkit Agrawal and Deepak Pathak and Alexei Efros and Trevor Darrell is this idea that you might use things like reinforcement learning, but think about an epistemic reward function rather than being a typical kind of utility reward function. So if you're looking at that little boy, what he seems to be driven by, what all 2- and 3-year-olds seem to be driven by, is get more information, find out as much as you possibly can about the world. And what we're trying to do, we, of course, being the graduate students, being Deepak and Pathak, is to actually build in that idea of information gain into the system itself. And we can characterize all of these things in computational terms. So having higher temperatures, broader proposals, flatter priors, and in particular, having these epistemic utility functions might be something that would make a computer that fulfilled Turing's initial promise, a computer that actually was able to learn as well as a child could. And let me end by saying, of course, this all depends on all of our exploratory children, namely the graduate students, and then all of our protective caregivers, namely the funding agencies. So let me acknowledge that, and maybe we have time for a question or two. Trevor?
We certainly have time for a few questions.
Thank you for the great talk. And in Japan, we are short of kindergarten teacher.
Right.
So there is some project working on developing AI robots to teach children in the kindergarten. And I know in some specific applications it should be useful, but generally, do you think it's a good idea or a bad idea?
Well, this is the whole other piece of what I was talking about, which is this ability to do social learning, which we know that the kids, and I could give a whole other talk about this, which we know that children are extremely good at. It turns out that children are very good at picking up very subtle signals from teachers about what kinds of information are important or are not important. And I think it's extremely unlikely that anything even vaguely approaching that would be implementable in any of the AIs that we know about now. So insofar as children are actually, when children are dealing with teachers, there's these very complicated pragmatic interactions between the teachers and the children, which are actually allowing the children to learn as much as they do. And a whole other talk could be, how could we implement some of that in allowing robots, for example, to learn from human experts? And people are trying to do that, but it's really, really hard. In fact, on the other hand, there's some evidence that even having human kindergarten teachers may not be such a great idea in terms of children's learning. Because if you think about this explore-exploit trade-off, in education, this is a constant battle and a constant issue. And part of what's happened in early childhood education, for example, now, is that there's more and more push to have things like assessment very early on. And what this kind of work suggests is that that's going to be counterproductive. That trying to get the system to, say, do well on an academic score, that's exactly the kind of thing that is not going to allow you to do this kind of wide-ranging exploration.
Any other last question? If not, I could probably put in a plug for Alison. If you want more of her great wit and wisdom, she has a forthcoming book and an ongoing column in the Wall Street Journal.
That's right, yeah.
So you can follow her there. All right, thanks everyone. Let's thank Alison again.
Thank you.